Hello, and thank you for joining our Nuage Networks webinar today. My name is Dave Twinam. I am a Principal Solutions Architect with Nuage Networks, and I am going to give you an introduction to our product offering today, give you a little bit of a understanding of what the product is capable of, what the intentions are behind the product, what are the problems that it solves, and a little bit of some of the details of how the product actually works. So I have a lot of content to cover in really a fairly compressed period of time, so I'm going to ask to hold questions until the end, but you can submit them along the way, and then I will gladly answer as many questions as I can at the end of the session, and those that I'm not able to cover at the end of the session, I will gladly cover I'll follow up with you via email and answer those questions directly. So with that having been said, let's go ahead and let's get started. So the Nuage solution is first and foremost all around solving problems primarily focused on the data center. And the data center is a market which Alcatel-Lucent traditionally has not had a lot of experience with. So Nuage Networks was actually created as a wholly owned venture of Alcatel-Lucent to address these specific challenges in the data center that Alcatel-Lucent saw. So specifically, we are wholly owned by Alcatel. We're actually headquartered in Mountain View, primarily staffed by a lot of folks from the IP routing division from within Alcatel-Lucent that actually developed the original SROS code base, which represents the software system running on the 7750 router family. So the software base has 10+ years of development. It has all the QA work, the scalability, and the features required for the largest carrier networks in the world. We've taken that as a code base on which to base the Nuage solution, but we've combined that along with some of the additional and newer techniques around the lines of network virtualization. We've combined that with the expertise that Alcatel-Lucent brings in building very large-scale IP networks, again, the internet being a great example. It's a little known data point that Alcatel-Lucent actually maintains the #2 market position in terms of port density in the internet today. And so there's a huge amount of expertise there that we're able to tap into. And then something that's truly unique to Alcatel-Lucent that we've actually brought to bear in developing the Nuage solution is the fact that Alcatel-Lucent also has a tremendous amount of experience in building very, very large mobile networks. And so we think mobile phones. And understanding the techniques that are used there to provide scalability, to provide mobility, and really that is all around making it a policy-based infrastructure. And it's a very different way of viewing problems than we traditionally have in, say, the campus or the data center infrastructure. And it's how do we actually solve those same problems using a policy-based mechanism to achieve the same level of scale along with the virtualized network components and virtualized server components that are actually present in today's data center, to actually bring those all together into a cohesive solution. That is the Nuage solution in a nutshell. And the term SDN, or software-defined networking, is, in our opinion, a very overused and abused term, and that it seems like every vendor has adopted whatever their solution was has now suddenly become an SDN solution overnight. This is different in that it was inherently a solution which was leveraging some existing technology and some existing knowledge, but is really being brought together to actually build a truly software-defined solution. And why I say that in the way that I do is that this solution is entirely software-based. It does not require any Alcatel-Lucent hardware for it to work, and as we'll talk about in some coming slides, it's actually independent of the network infrastructure underneath. So it truly is software-based and really taking SDN networks into a form of reality where this is something you really can build versus something which oftentimes seems to be kind of hyped a lot and not necessarily delivered upon. So leveraging all of these common technologies and applying it to what is commonly known as SDN, and actually something that is actually being delivered upon today. If we dig down a little bit deeper into some of the more of those technical details that we kind of high-level addressed in the previous slide of traditional data center designs, we typically have this common orientation around pods. In this case, I have 2 pods with 3 racks each. They have a top-of-rack switch at the top of each rack. Those, in turn, actually are dual-homed up into a pair of aggregation switches, and the pair of aggregation switches, in turn, is dual-homed into a pair of routers. And in order to connect between these pods, I either have to have extended layer 2 environments, or I have to actually route between the pods. So pretty common infrastructure. You typically will see that within a given rack, you will likely have some form of layer 2 connectivity inside of rack, and then oftentimes it's layer 3 in between the pods. So within a given pod environment, you're going to have typically the ability to have extended layer 2 inside a pod. Oftentimes the traditional design is that those pods are actually separated by a layer 3 boundary, so you have to route in between them. So if, for example, you want to perform something like a VM migration or a vMotion, those are classically restricted to being inside a layer 2 contiguous segment. So if that's at a pod level, then it means that within those racks within the pod, I can move anywhere I need to. But if I can't actually move in between the pods because I don't have layer 2 extended, then that's a different problem scenario that requires additional engineering techniques to get around. I typically have, classical VLAN segmentation, so I have 4,000 VLAN IDs to work with. You can have limitations on the number of VLAN IDs, especially if you're a service provider. You can only have 34,000 customers at that point. What if I have overlapping VLAN IDs? Am I using a multi-chassis lag for that aggregation device upstream? And if so, does that lock me into a given vendor? Are there any kind of scenarios that end up with suboptimal traffic patterns across that multi-chassis lag where maybe only one of the two chassis is actually active for a given VLAN? Classical scenarios along these lines that are difficult challenges that we oftentimes have learned to kind of accept and deal with, but the reality is they do actually provide us with a lot of challenges in terms of being able to leverage the true capabilities of the compute resources and the applications that run on them. Some of the other inherent challenges, things like the number of MAC addresses has exploded in the data center, and really the cause for this is that we have server virtualization. So it's no longer one MAC address for a given server. It's multiple MAC addresses being represented behind it because you have a large number of virtual machines now represented behind that physical host. So I have to understand, do I have actually the table space to do it? I can buy less expensive top-of-rack switches, but in some cases they can't actually support the VM density that I would like to achieve for ideal resource utilization. So how do I overcome those challenges? And then we've talked about the VLANs and the subnet alignments and some of the challenges inherently provided by those, or the limitations, I should say, that are inherently present with those techniques. So you oftentimes end up with, asset isolation. So I have underutilized resources in the racks on the left, overutilized resources in the racks on the right, and I would really like to build a load balance in between the two. And it's not necessarily all that easy to do because of, again, some of the classical network infrastructure challenges. Can it be done? Absolutely. But oftentimes it's very complex. It may not be easy to actually provision those in a timely fashion. It may take a lot of specialized effort, meaning I have to map all those ACLs. I have to actually port them to devices. It requires logging into those devices, making the changes versus something that is truly dynamic in the forms of, say, VM creation. And oftentimes your growth constraints are all around the size of the pod, and if that pod size changes, you have another layer of problems you actually have to now overcome. So the next challenge is that if I have two or more data centers, I have these same fundamental problems now, but compounded in between data centers. And so there may be the classical, I want to have things like a disaster recovery facility, whereby I have the ability to migrate resources that are in data center A on the left to data center B on the right. How can I actually migrate that VM? Do I have a layer 2 extension capability in between those environments? Maybe I have something like a VPLS network in place today, but then how do things like MAC learning work? Is it limited for certain applications that work and certain applications that don't? Do I have the ability to have true disaster recovery, meaning it works for layer 2 and layer 3, or is it limited to one or the other? How do I have the ability to dynamically provision these services, meaning that if I want to actually dynamically extend a network in between data center A and data center B, how does that actually happen? How quickly does it happen? How many steps are involved? How many people have to be engaged in order to actually program that connectivity and maintain that connectivity? Or is it truly dynamic in nature? What if I have an existing VPN infrastructure and now I actually want to actually tie that into an existing cloud network, or I want to actually buy cloud services from a provider and extend that into my data center? How do I actually connect the two? What are the challenges? Or am I restricted to layer 2 or layer 3? Does it work with the current VPN technology that I've chosen? And all of these are inherent challenges that one has to consider when trying to actually connect these data centers together. These are all aspects of the solution in addition to the problems we talked about on the previous slide of the data center of the Nuage solution and problems that we can actually help you solve today. So one of the key changes to understand of why we're actually seeing some of these challenges is, number one, it starts with the cloud. Right? And our definition of cloud in this circumstance is really it's any resource, anytime, anywhere. And I think that's important because I don't think actually everybody necessarily views it the same way, but I think that usually as a consumer of a cloud, that is typically how we want to view it, which is we really don't care about all those infrastructure problems that we talked about on the previous slides. What we do care about is that if I'm running an application in the cloud, I want to make sure that it's always available, and it's always available anytime that I need it to be available. And you really don't care about all of those network challenges that are present within your provider's environment. You just want to be able to access it. So the cloud is fundamentally changing the way that technology is being consumed, because in the past we didn't have that level of flexibility. Right? The traditional has been that I go on to a user portal, a service portal of some form, and I actually place an order. Then I have to wait for my order to be fulfilled. In a traditional manner of turning up network services, sometimes this actually was in the order of weeks or even months, sometimes for new services to actually be created. And we've actually become very much about instant gratification. And so we expect that if I'm going to place an order, I'm going to immediately receive my services that I've ordered. Right? And everything has become much more multi-tenant. Instead of being a single person that actually was in charge of actually administering all these components and engineering them, now it's all become about how many different users can access it so that we can actually make this very personalized and much more dynamic in nature. So the expectations have changed, and as a result of those changes, the network now needs to change as well. So one of the other keys, and it's very closely tied to the previous slide, is that the technology has actually changed. So in that previous example that I gave on the last slide, we talked about how you expect this instant gratification. And if you look at some of the ways that we actually go about dealing with our, whether it's professional or personal interactions anymore, we expect more of that instant gratification. And oftentimes there's an abstraction in between the what and the how we actually go about gaining access to whatever it is that service that we're ordering. So if I'm placing an order online, I can place the order. How it actually gets to me is really fairly irrelevant. I really don't care as long as it comes in a timely fashion. So there may be any number of fulfillment vehicles that are present that allow me to actually gain dynamic access to those resources. And ultimately, there's a level of abstraction, and then there's a series of automated functions in between that are transparent to me as the end user. And that's the way that actually networking needs to become as well, in our opinion, which is as a consumer, I know what I need. I don't really care how it's fulfilled at the end of the day, as long as obviously it's secure and I'm not running into any issues as far as inappropriate access to data or any kind of reliability challenges. So assuming that all of that is covered, all I really want to do is make my request, so provide my needs, and then the means are actually automated and dynamically delivered directly to me. So if I look at the data center network, again, we're all about, you've got virtualized compute, and things have changed in that now I have a tenant that actually creates a request for an application. And that application doesn't necessarily care about the configuration details of the network. What they care about is the actual application running against the actual compute infrastructure. So the network is partially virtualized. Some of it is there. Obviously, you have virtualization capabilities in terms of, say VLANs, for example, which is something we've been using for many, many years. But the challenge of that is still very much static and manual in nature. There can be some automation in the form of scripting, but really, most of the scripting is still calling out CLI commands, which is just kind of automating a manual process. But fundamentally, it typically takes a long time. What we find is a commonplace scenario for a lot of our clients is that they can turn up a virtual machine in a matter of minutes. But to get it actually connected to the network may take actually weeks or months, and that's because there are multiple steps that are required. So I can fire up a VM, right? And maybe it's a second that it actually takes in some circumstances to fire up a new VM request. That's a very simple request for anybody on the kind of the system side of the house to actually initiate and execute upon. The next challenge becomes now, as it actually gets kicked over to the networking infrastructure, you know that then you have to figure out, all right, what are the VLAN mappings and the subnet mappings that go to the VLAN, and then understanding are there security implications, and so what ACLs need to be configured, and what are the correct QoS policies that need to be defined, and are the firewalls needing to be modified to actually support this new application, and what are the requirements now for my LAN and my WAN, and all those different aspects that actually need to be programmed, and those changes need to be made, and those processes are very much manual in nature. And this is where we go from that instant gratification of I can turn up a VM automatically and instantly, but to actually work it through the network infrastructure is very, very challenging. So my actual time to actually create a new service is hindered by the actual manual nature of the network processes that are required. So, and we know that these functions are all important, and we can't make any of those functions fundamentally go away in terms of we need to have those configurations in the network present, but how do we actually go about automating it, and is there a new way for us to actually look at actually having this happen in a much more dynamic fashion? The next key here is that whatever we do in this regard to solving these problems, it has to be very much an open solution. And this is very much the focal point for the Nuage solution, which is that we're very much agnostic to the actual infrastructure itself, meaning we don't really care who the server hardware is. We don't have any restrictions there. We don't want to impose any upon the actual end user of what compute is required. The same is true of the actual hypervisor you choose. We support VMware's ESXi today. We also have support for KVM. We also have support for Zen Server. The only major hypervisor we don't yet support is Hyper-V, and that's really just a function of we haven't seen the customer demand for it as of yet, but we have no issues actually supporting that in the future as well. Right? We're agnostic to the data center networking hardware, so it doesn't matter whose routing and switching infrastructure you're using underneath this. We will support any of your existing infrastructure, so this is very much about both brownfield as well as greenfield deployments. We have to be able to operate over the network infrastructure you already have. So this solution, again, is a software-based solution that works over any vendor's network infrastructure. As long as it is IP-based and it is reliable and scalable, then we can actually operate over it today. Right? We also don't care what compute virtualization environment you have selected. So if you're a VMware shop today and you're using vCenter, that's fine. We can work with it. If you are interested or deploying OpenStack or CloudStack, we have support for those CMS offerings as well. We also expose a northbound RESTful API, meaning if you have another tool that is not one of these tools that you would like to integrate with, or maybe you have a combination of the tools, we have the ability to also integrate directly with those solutions today in a very much of an open systems approach to data center networking. The key is how do you actually make it very consistent and offer the same capabilities regardless of which choices you have made, all the way from your server hardware all the way up to the actual compute management solutions. So let's talk a little bit about the product at this point. The Nuage solution, which we call the VSP for the Virtualized Services Platform, consists of three primary components. Those are the Virtualized Services Directory, or the VSD, the Virtualized Services Controller, or the VSC, and then the VRS, which is the Virtualized Routing and Switching element. So if we start at the top and work our way down, we have the VSD, which is essentially your network policy engine. So think of this as your management plane. It is where you actually define all of the policies that are going to apply for the components which reside beneath it. So from a management perspective, this is where I'm defining who can talk to who. This is where I'm actually going to define things like actual subnets when we get into those details a little bit later on. But more importantly, it's about creating a layer of abstraction. And we do that because we want to abstract away from the complexity, because too often we focus on the complexity and we're not actually solving the business problem. And this is about, let's solve the business problems for the required applications, and then we'll worry about the actual complexity by putting a layer of abstraction in between, because the complexity comes a little bit later, and we can do that in a much more simplified manner. I'll give you some more examples of how this works a little bit later in the presentation, but essentially what we're going to do is we're going to create templates. If we know that there are certain traffic patterns that are always required for, say, a 3-tier web application, we know that we have to offer access to the internet directly from that web server. behind the web server, we know that we're going to restrict the access from that web server back towards, say, a business logic tier. And then we know that we have restricted access between the business logic tier and the backend database. It's simple enough for us to actually define what those flows need to look like. And we can do that in a manner before we've actually even done things like allocate IP address space or VLAN IDs, because ultimately those are details that come later. The key is what's the actual business flow for the application. There's obviously a network element to it, but the gory details of the network elements can actually be attached to this template at a later point in time. The next step is the actual VSC, or the controller. So this is your control plane. If you think of a classical router, you have at its simplest form a control plane and a data plane. So your control plane being it's your routing protocols. And in this case, because we're actually leveraging SROS, our controller runs that same code base of software that comes from the 7750 router family. So it doesn't mean that it's big and complex. It means in this case it's actually the same software innards, essentially, that are running now on an x86 platform completely in software, but with all of that feature scalability, the robustness of those characteristics that are actually applied to carrier-grade networks, but now running inside a virtual machine, providing things like ISIS and OSPF and multi-protocol BGP communications, which gives us the ability for our controller to talk directly to the network infrastructure. We also have the ability to use those same characteristics and protocols to actually give us a high degree of scalability and reliability. So I have the ability, for example, to have multiple controllers either inside a data center or between data centers communicating via multi-protocol BGP, allowing me, just as I would scale routers in the internet, to scale my controller solution out very effectively. So this gives you, again, scale and reliability, redundancy at the exact same time. So this is your control plane. The control plane, of course, then communicates and actually programs the forwarding path of the data plane element, which is the VRS. The VRS, again, is a software entity. In this instance, it is actually based on Open vSwitch. So you have a VRS element, which is an OVS-based element along with our software that now runs directly on your hypervisor. So we're replacing the vSwitch that might have been there previously or augmenting that vSwitch in the future with a VRS element, which is our software, that gives us now the ability to have fully distributed layer 2 through 4 rules propagated all the way down to the vSwitch level. What that means is now as traffic actually comes out of a virtual machine, it goes to the VRS, which is our vSwitch sitting on your hypervisor. That then can actually determine and push traffic in the appropriate direction based upon the policies that you've defined all the way up at the VSD level and have been propagated down to the VRS. I'll give you more examples of how this works in a few more slides, but the key here is, again, management plane at VSD, control plane with the VSC, which is, again, all your control plane protocols, and then the actual forwarding element takes place down at the VRS. I also have a solution for integration of bare metal resources, and I'll talk about that in a few more slides. But the key here is that you may not have all of your components running inside VMs today. And how do I actually allow for connectivity in between those VMs and any of those bare metal devices that have not yet been virtualized or may never be virtualized? And we have a solution for that that's shipping and available today as well. I'll talk a little bit more how that works in a few more slides. So I want to give you a little bit more detail of VSD, and that all I gave you on the previous slide was a very high-level representation of what the VSD is capable of. It's actually capable of quite a bit more than that. So the VSD, again, is a software entity. It runs as a virtual machine, meaning this runs as a piece of software on top of an x86 platform. And it is actually where you establish your service definitions. This is where you define your policies and where you build the templates that I alluded to on the previous slide. So again, I gave you an example of the templates of perhaps a 3-tier web application or whatever your application requirement may be. The components of that template are going to be defining, how many networks do I need, how many subnets are required for a given application, what kind of policies are required for communications within and between those particular subnets. And I have multiple ways that I can actually build those. I can actually define zones. And the zones can be defined based upon your business requirements. And so whether those zones are application-based or whether they're following network policy-based, whether they're actually, say, business policy-based around like your organizational constructs inside your company, Any of those can be used as different mechanisms. I can define quality of service characteristics, so I can have application priorities. I can also define things like rate limiting characteristics if I want to limit the amount of traffic that a given application type can consume or a given tenant can consume in the environment. I have the ability to do that, as well as complete statistics collection. So, and I mention this because this is also something that's important and lacking in many of the offerings that other vendors are talking about today, is that they don't have ability to accurately understand the actual amount of traffic that's actually flowing through the network and that type of traffic. And doing so in a highly scalable manner, we've actually done this by the inclusion of an optional Hadoop cluster that can actually be added on top of this platform in order to give you full access to statistics within the platform. Or if you're looking at it as a provider, the ability to actually generate billing data based upon this. Or perhaps it's just billing data or usage data back to the actual end users of the environment so they actually know exactly what is being consumed, which is also critical. This is also your interface back into the various CMSs. So I mentioned previously that we have a northbound REST API, which gives you the ability to actually access any of these components inside the VSD. So anything that can actually be controlled by the VSD can also be controlled directly through the API. So you can make these calls either through one of those existing systems like a cloud stack, a vCloud, or an OpenStack, or via a third-party tool. We also have the concept of user hierarchy as well, which gives you the ability to define users that have different capabilities. So there may be those users that just need to be able to view the policies or view the statistics, and then there are those that can actually configure and make changes to those. And we'll talk a little bit more about how that data flow actually works. But the key is it's defined inherently as a multi-tenant solution. So if you don't want to have thousands of different customers, or maybe it's 10 customers, it doesn't really matter to us. You have the ability to give them all their own appropriate representation and access to the product based upon those overall policies that you define. Now, the policies that we define either in, say, an OpenStack or a cloud stack or directly through the actual VSD interface are all created on the VSD, then they're propagated to the VSC or the controller over XMPP. And the XMPP, if you're not familiar with it, is actually a message bus-based protocol, which is, at its heart, also the infrastructure used behind some of the more commonly deployed chat protocols in the world. So if you look at something like an eJabber, which you may be used to using for instant messaging, it's the same infrastructure. The reason we chose it, number one, it's open standards-based. Number two, it's highly scalable. Number three, it's secure. The beauty of using XMPP also is that, again, it's a message bus, meaning if I send the message out, it goes onto a bus, meaning it gives me instant access to multiple controllers, which, again, gives me a high degree of scalability. We had to choose something which would give that inherent scalability, and as well as a component of being highly parallel in nature out of the get-go, and that's something that we can provide today in the VSD. So these policies come to the VSC. Again, the VSC is our controller platform, so it's the control plane of this routing infrastructure. It is also a software-based entity residing on a virtual machine running on an x86 platform. So again, it is based on SROS, so SROS being the core operating system of the Alcatel-Lucent routing IP products. And so we leverage that as inherently 10-plus years of software development, QA, all those characteristics that come into it. So it's not a brand new stack, meaning it's not something that needs to actually be vetted still in the environment because it's actually been very well vetted in the largest service provider networks in the world. It inherently gives us access to all of those basic SROS characteristics. And so whether that is an inherent CLI characteristic or whether it's access to things like SNMP, full routing protocols, both IGPs and EGPs, all those characteristics are already there. It gives us the ability to inherently create federations and peer between controllers, which gives us scalability and reliability inherently. Again, just in the exact same fashion that we actually gain that level of scale in internet routing, we're leveraging those same characteristics. There's no need to reinvent the wheel and reinvent new protocols. What makes more sense is to actually leverage what's already been exposed in the internet and proven to be highly scalable in nature, and that's exactly what we've actually leveraged here. We have the ability to create a multi-tenant environment inherently. So just like you have VRF instances today, and think of that in an MPLS type context, we have the same context here because again it's the same software code base that we're leveraging. So you can have multiple VRFs, which looks the same as multiple clients. That can be multiple departments, say, inside a given customer environment, or it may be actual multiple customers if you're looking at this as a service provider type platform. The communications, again, back from the VSD are all over XMPP, that Open Systems Messaging Bus, and we use OpenFlow as the actual mechanism to push the actual forwarding rules down to the VRS, which is the next element that we'll talk about. It's important to note here that the VSC, again, is a routing control plane. So we have a RIB and a FIB, as you would expect in any router. We actually compute the RIB, because it's a full-blown router, inside the VSC. We then push the FIB, or the forwarding information base, as it is appropriate down to the VRS. And what I mean by as it is appropriate is that a given virtual machine doesn't need to have a complete internet routing table, for example. We know that that doesn't scale. We have the ability to push just the actual forwarding information base that is required for that particular VRS down to that particular element, giving it a high degree of scalability and optimizing the resources there. So we're not wasting a lot of resources. Now you'll notice on the right-hand side of the slide, I also have references to, in this case, security devices or load balancing devices. So we are not inherently a firewall. We have some firewall characteristics in that we have the ability to push full ACLs down to the actual VRS element, but that's not the same as being able to provide a truly stateful firewall with all the characteristics that that appliance can provide. So we also have the ability to integrate with those platforms. So we can do this in several fashions. Either we can just hand off to those devices in a natural fashion should the traffic flows allow for that. We also have the ability to create what we call service chains, which is the ability to create policy-based routing rules that allow us to, based upon a given rule set, forward traffic inherently to one or more appliances and create a chain. So for example, if I know that any traffic that is going from a particular source to a particular destination, I want that to make sure it gets processed by a firewall, I can inherently install a rule that will require all traffic A to B to go through that firewall. Furthermore, I may decide that assuming where it comes out of the backside of the firewall, it then needs to be processed by a load balancer. I can create that service chain element as well. And then perhaps I want to process through an IPS or an IDS or some other appliance in my environment. I can also create additional levels of a service chain to ensure that traffic flows as appropriate. Part of why this becomes interesting is that what we see increasingly is that if I know I have a lot of east-west traffic inside my environment, I may realize that, well, if I know that it's already inside this environment and it's okay, I don't actually want to force all that traffic through my firewall, because my firewall may only, say, be running at 10 gig. And it becomes ultimately a bottleneck for my environment, given that all these servers are also attached to 10 gig. So if I don't need to process traffic on a firewall because perhaps the ACLs down at the VRS element are sufficient, I have the ability to limit the traffic that has to be processed by the appliance, therefore giving me a much greater degree of scale for that appliance. So perhaps that appliance is adequate to now scale for my entire environment for internet-based traffic, and the rest of the traffic inside the environment is adequately still provided for from a secure fashion via ACLs. So the same can apply for other appliances as well. So again, the last step of the controller, I build the RIB and the FIB, and I push the FIB down via OpenFlow to my VRS element. The VRS, again, is a software-based entity running in the form of an OVS or an Open vSwitch piece of software installed directly on the hypervisor of my virtual machine. So this gives us the ability to actually have all of that vSwitch capability that's required for forwarding traffic in between VMs or between, or locally within a given server, or between VMs that are on different servers, or even between a VM and, say, the outside world, the internet, for example. So all of that inherent forwarding characteristics are actually provided inside the VRS. So this is the actual forwarding tables as well as those ACL rules which are applied on top to actually determine how traffic is forwarded from a given source to a given destination. Now, the way that we actually provide this in a fashion that is transparent to the underlying network is we actually build what's called an overlay network. So we're actually going to tunnel traffic in between virtual machines such that I am no longer bound by limitations of, say, subnet boundaries or VLAN identifiers, because I'm actually going to put a tunnel header on the front of that traffic and tunnel traffic between endpoints. So the network infrastructure underneath now becomes transparent to the actual endpoints participating in this overlay network. Now, the techniques that we have selected are both VXLAN and MPLS over GRE. So the reason for those is, number one, they're well-defined standards. We don't want to do anything that is proprietary. VXLAN gives us the ability to inherently put a VXLAN header because it's inherently based on the OVS software includes that VXLAN capability. So we have that ability to actually map and create these tunnels end-to-end, defining that connectivity. We also have the ability to use MPLS over GRE to connect to those devices which may not yet be VXLAN capable. So we don't necessarily have a preference over why you might use one particular tunneling technique or another. The key is to actually provide a tunneling characteristic that is present in your network infrastructure without requiring any, say, hardware upgrades to do it. So MPLS over GRE, for example, is a well-defined standard that is present on pretty much the major routing platforms, whether it's like a Cisco or a Juniper or an Alcatel-Lucent today, meaning if I actually have to integrate directly into an existing router to participate in this infrastructure, I have the ability to do so with any of those third-party devices. Now, as those devices actually incorporate VXLAN support, you may be able to do everything with VXLAN instead of MPLS over GRE. But the key is that the vast majority, if not all of those PE routers today, do not yet support VXLAN, as it is a newer emerging standard. So we have multiple overlay techniques that we can actually use based upon the requirements for a given infrastructure. We also have the ability inside our VRS element to actually detect new VMs actually being created as well as when they're actually being destroyed, which gives us the ability to dynamically then actually map the overlay network as required and respond directly to these actual changes in the network infrastructure. This will become a little bit more clear as we actually work through a data flow of the actual product in use, but these are the core three elements that provide the VSP. So I mentioned earlier that this was all about taking a more policy-based approach to networking, and that's really where we were leveraging some of those characteristics that we've learned from working in mobile networks. And so how do I move towards a don't keep designing the same thing over and over again? Why don't I come up with a good, solid design the first time and then create a template from it and reuse it as many times as possible? So, as part of a template, you have, key things like your business rules. You have the application types, which are going to leverage those business rules, and then you have the consumers or the users of those particular applications. So now what happens is I can define a template. So it's a policy-oriented template. So I know who can talk to who. I know what port numbers are allowed, what application flows are required for a given application to function properly. I can actually then evaluate that policy and then map it into a template. So in this example, which is probably not the easiest to see, but I've created a 3-tier web application. So I know that at the top of that, I have a router that connects to the internet. The traffic that comes through that must flow through a firewall, where it then hits an interior router where I can actually access my web resources. And then obviously that's probably all going to be filtered on port 80. Then coming out of my web server back towards my business logic tier, I'm going to process by another firewall. The business logic is going to have restricted connectivity from the back end there into, say, my database tier. And then I have a reverse flow traffic through. I define this policy. I define the users that can administer this, that can view this traffic. I know what applications are allowed, and I know all the policies. But again, I haven't actually even mapped it into a network just yet. I've defined policies with templates. And those, in turn, will actually get processed by an actual roles-based workflow. So in this case, I have a CMS system, maybe like an OpenStack or a vCenter, what have you, that's actually going to spin up new virtual machines. It's going to request new resources on the network infrastructure. So I have an application request that comes in from a tenant, which gets processed by the network in terms of I'm going to create a new virtual machine. That new virtual machine has to actually access the network resources. As part of that, we know that requires things like IP addressing schemes being enforced. I have to have ACL rules. Perhaps I have particular security requirements for that application, meaning that the traffic must be firewalled, it must be load balanced, it has to be processed by an IPS. All of those service chains can be auto-created. I can actually define those security zones. All of this actually happens in a completely automated fashion. So again, I create a template. The template contains the business logic and the policies that are defined. Now, as users actually consume that template, we dynamically map that into the network infrastructure and create the appropriate flows that are required all the way down to the VRS level elements, meaning we create that overlay in a dynamic fashion. So as we talked about early on of what were some of the inherent challenges we were trying to overcome, it's all about abstraction and automation and how do we actually reduce that time to market. And that's something that we've actually created with our VSP. So what I'd like to do is give you an example of how you actually go through provisioning services now. And I'll walk through an example fairly rapidly for you. So step one, I have a user that is actually working with our VSD. Now we do provide a web-based user interface for the VSD. It's primarily there, frankly, for the purposes of demonstrating the capabilities of the product, because we expect that a lot of our customers are actually going to want to define everything through the API instead, meaning they may be using Cloud Stack, they may have vCenter, they may have a combination of the above, or they may have some homegrown tools they want to use. If they want to use those, that's great. We're fully supportive of that. That's why we actually built this the way we did. And in fact, our user interface actually uses our own REST API. So it's actually leveraging the exact same tooling that you could in turn leverage if you wanted to. So what I'm going to do is I'm going to actually create one of those templates, one or more of those templates that we talked about previously. So those templates are created. I know within a given template I'm going to have maybe certain zones of connectivity based upon the application requirements. I may have, for example, a web zone, a business logic zone. I may have a database zone. I have users that are going to be mapped and what those users are capable of operating on this template. I know what my internet policies may be for connectivity. I may have a VPN that I need to connect to as part of this. All those characteristics are actually defined inside that template at the VSD. The next step becomes that I'm actually going to create new compute assets. So I want to spin up new virtual machines. So this particular example, I'm leveraging OpenStack. It could be any of these tools. It would not change anything other than just where the little bubbles would appear on the diagram. But logically, it works the same. So OpenStack is actually going to create a request for new virtual machines to be created. I'm now going to create those new virtual machines. And again, OpenStack is actually, in this case, triggering that creation. So it uses the same OpenStack affinity mechanism, which decides that, okay, on these two servers, I want to create these two new virtual machines. Those two new virtual machines are now instantiated or created running on those particular hypervisors. Just creating them doesn't inherently give them network connectivity. So just as in the examples that we had described previously, that I can create new VMs, but it doesn't mean that they can use the network right away. That's actually true here. However, the actual process to get them on the network is now fully automated using those policies that I've actually defined in the templates previously. So what happens in this circumstance is that these new VMs have now been created. When the new VMs are created, they will be seen by the VRS, which again is that vSwitch running down on your hypervisor. When those new VMs are seen, that VRS is going to look at the characteristics or the metadata associated with those virtual machines and realize that it doesn't yet actually have a forwarding policy for those particular VMs. So it doesn't know how to forward traffic correctly. So it will actually send a query upstream to the VSC over OpenFlow that says, I need to understand how to actually forward for these new VMs that I've seen. The VSC will consult its policies, realize, nope, this is brand new, we haven't seen it before, and actually propagate that request, in this case over XMPP, back to the VSD. The VSD will now consult its policy and realize that it has a template and a policy associated with that template that you created previously. And it will propagate those policies back down to the controller. The controller will then compute the RIB and the FIB based upon the policy and the template it just received from the VSD. And that FIB, in turn, is pushed down to the actual VRS elements. The VRS elements then have the ability to actually now build a VXLAN tunnel directly between them. So now any traffic that needs to go between those two VMs will be inherently encapsulated inside a VXLAN tunnel and directly propagated between the VMs. If any of that traffic had to go to the outside world, it would actually be directed directly to your next-hop gateway router, and that gateway router is not anything special in our environment. It's actually just your next-hop PE router. So, and again, that's where I might use either VXLAN or AMPLS over GRE to that PE router in order to give connectivity to it, where it will then inherently forward it without any tunneling encapsulation on the back end. So this gives me my connectivity inherently. I can actually continue to add new devices to this. In this case, I've actually added a third device. So I can add n number of devices, and as those new devices are created, the only step that changes is they don't actually have to actually bounce the request all the way up to the VSD, because now the controller inherently has that forwarding information already. So now the new VMs get added directly by forwarding a request to the VSC. The VSC propagates the appropriate FIB to the VRS, and new elements are added to the overlay network. This happens in seconds or sub-second time frames. This is very, very rapid because it's all predefined at this stage. So rapid introduction, inclusion of new devices on the network environment. So I can do the same thing with multiple data centers. So now in this case, I have 3 racks or pods on the left-hand side. I've actually added now a new rack in a new data center that is physically in a different location. So it is likely that if I'm actually going to add a data center in a new location, I'm probably going to add a new controller as well. Whether it's for scalability or reliability, I'm going to want to probably have, again, just like you would have another router in that data center, I'm going to add another controller. And again, the VSC is just a software entity running in the form of a VM running on an x86 platform. The VSCs, you'll see, actually create a federation between them. They do that by actually running multi-protocol BGP in between them, which allows them to exchange routes and exchange policy in the same manner. So now I actually have the ability, because my VSCs are federated, I propagate my rules, I propagate those policies along with the rules, and those actually get pushed down in the form of a FIB to the local VM, or VRS in this case, running inside the new data center. Now my overlay is inherently extended. All of this can happen transparent to the underlay network, so that existing physical infrastructure you have in place has not been inherently required to change to accommodate this new capability. The next logical step is I continue to build upon this and build more complex environments. I may have n number of data centers. We can scale to any number of data centers you need to continue to require. Again, it's leveraging BGP controller federation. Look at the route reflectors. It's the same techniques if you're familiar with BGP route scaling. You also have the ability to integrate bare metal devices into this environment. We can do that in a couple of different forms. So you'll notice if you look carefully right at the center of the slide here, there is actually something called a Nuage 7850, which happens to be a Broadcom Trident 2 based platform that looks like a top-of-rack switch. In this case, it's not really intended to be a top-of-rack switch replacement. It's really intended to be a gateway service. What happens is we map on a physical port level for every physical port that connects to a downstream bare metal server. We run software against that physical port on that hardware platform, which actually performs the capabilities you would normally expect for a VRS, giving us the ability to extend and overlay directly from all of those bare metal devices and include them into this environment. It's also important to note this environment can inherently be a multi-hypervisor environment. It could be any combination of ESX and KVM and Xen and bare metal all combined into the same overlay or n number of overlays. We also have the ability, because of the inherent characteristics of SROS, to integrate directly with your PE router. Again, that's where the MPLS over GRE or VXLAN comes into play. By offering that level of integration, we can then map directly at VRF level into, say, MPLS VPNs on the backside of that router and give you direct integration into an existing MPLS cloud or into an existing MPLS VPN service. So a great degree of flexibility and integration with existing environments is key here. So, and last, just to kind of, touch upon that again, the ability to offer a true overlay extension such as VXLAN. This is something we can inherently do today. This is not a problem. We can, again, transparently do this via VXLAN from node to node. There are those that may not want to do that because perhaps they actually want to, say, firewall the traffic in between those sites, and that's fine. They may want to actually do that via more of a layer 3 oriented service by integrating with an existing MPLS VPN, such as I've actually shown at the top of the slide. So again, the characteristics are the same regardless. It's just a level of integration that's required. And again, we do this in a completely open standards manner, existing with existing platforms in your environment today. So this is both a brownfield and a greenfield opportunity for you for inherent virtualization of overlay environments inside the data center, as well as in between data center environments or existing cloud services, new cloud services offering true hybrid cloud. All of those are characteristics of the solution that we can actually bring to bear today. This is a shipping product. It has actually been shipping since May of 2013. That was the 1.0 version. We're actually up to 2.1. We'll be shipping in the April timeframe. We are actively engaging with customers today. We have production customers and deployments of the product today. We would be more than happy to follow up with each and every one of you if you would like to actually talk more about how we might be able to address challenges inside your environment with Nuage. We are actively engaged in lab trials and POCs with many additional customers today as well, and would be happy to engage in those further conversations with you. So this is kind of the quick introduction to the Nuage service offering, and I will gladly answer a few questions for you at this time. Thank you.